All right, good morning, everybody. It's a great privilege to introduce the first plenary speaker of this conference, which is one of the most influential persons in quantum science, Anton Zeilinger. Anton has, in the past 3 decades, performed a large number of really groundbreaking and by now famous experiments. You all know about teleportation, experiments in which he put small molecules through double slit experiment, making superpositions, and he received many, many prizes for that. I actually heard from German colleagues that in the German-speaking countries, Anton Zeilinger has a status that actually goes far beyond science. And maybe this is best compared to what Robert Dijkgraaf is for us in the Netherlands. So somebody who is often on television, who is really a spokesman for science in itself. And there's another similarity with Robert Dijkgraaf. Just like Robert was before, Anton is now president of the Academy of Sciences in Austria. So today, he is here opening our Congress, and he will do that by answering one of the most, hopefully answering, one of the most fundamental questions in science. And that question is, what is light? Ladies and gentlemen, please welcome Anton Zeilinger.
So, thank you very much for your kind introduction and for the invitation and for the insistence that I come. I cannot avoid adding something to the speech of our president, talking about roads and forks in roads. There is a famous quote by the American baseball player Yogi Berra. It's a general advice. If you come to a fork in the road, take it. So what you see here, I'm not sure if I can answer the question. I just refer to Einstein's question, what is light? What you see here on the first picture is on the Canary Islands, a telescope. It's not built for astronomy, but it is built to test optical communication with satellites. It's called OGS, Optical Ground Station, and it is used by us for testing optical communication on the ground for now to another island. You see a beacon laser here, a laser beam which goes over to the island of La Palma, 150 kilometers away. So here's Einstein, 1905. He wrote his famous paper, whose title you see at the bottom. I think it's similar enough to Dutch that you can read it. It is actually always explained as the photoelectric paper. The paper is mostly about something else. Namely, it's about the argument why light should be considered to consist of particles, namely for statistical reasons and for reasons of entropy conservations. Now, and this is very, very nice for a quantum physicist. This paper is the only one of his papers which Einstein ever called revolutionary. In a paper written to his friend Habicht in the same year. And as you all know, he got the Nobel Prize 1921 for that paper and never for relativity theory. A little later he said, I want to spend the rest of my life thinking about the question what light is. And we will come to where we stand now in that question. Now let's jump right into the discussion of entanglement. It goes back to this paper here, 1935, by Einstein, Podolsky and Rosen, with a philosophically sounding paper. Can quantum mechanical description of physical reality be considered complete? This paper was accepted by Physical Review without ever having been seen by a referee. And as soon as they sent papers to referees, he did not send them any papers anymore. For a very good reason. Namely, he said that the discussion between referee and author is a scientific discussion, and every scientific discussion should be out in the public. There's a point to that. Einstein, the basic point was that when you have two systems which interacted in the past, you can have a situation where the two states are entangled, connected in a way that measurement on one of them changes the quantum state of the other one independent of the distance. Einstein didn't like that, and he said, I cannot believe in this because physics should describe a reality in space and time without spooky action at that distance. Here is the development of my field over the year, as signified by the citations which the Einstein, Podolsky and Rosen paper received, according to the Science Citation Index. It came out in 1935. It received in the beginning only 5 citations, which were not bad actually. 2 citations were by Schrödinger, 1 was by Niels Bohr. But afterwards, nothing for a long time. So that paper would not have gotten Einstein a tenured position. Actually, if you want to look something up, it's very interesting. Look on Google Scholar, the page of Einstein. And there you see his age index, you see all this other nonsense about statistics, but you also see that his 2 mostly quoted papers are his 2 quantum papers, by the way. Now, then you see that the field slowly takes up. In the 1960s, when it was discovered that the Einstein-Podolsky-Rosen, when the Einstein-Podolsky-Rosen ideas are in conflict with quantum mechanics, and around 2000, a real explosion took place, which was because it turned out, to the surprise of everyone in the field, that entanglement might be useful in quantum information and quantum communication tasks. I will say a little bit about that later. Now the paper is quoted basically once a day, which does not mean that it is read more often than in the old days. Here's Schrödinger. Schrödinger came out in 1935 with the first thorough analysis of the new situation. He called the situation Verschränkung in German, in English entanglement. Verschränkung is a much better name because it's something like that, a well-defined connection. Entanglement is like spaghetti, it's not so well-defined. And Erwin Schrödinger said something important. I would not call that, namely entanglement, one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. And it's amazing that Schrödinger, who invented the wave equation and so on, thought of entanglement as being really the most characteristic notion. And in his analysis, he said something very, very interesting. He said that in a situation where 2 systems are entangled, you only have joint expectation catalogs. Expectation catalogs for joint measurements on the systems, but no expectation catalogs for the individual systems. And this is something which is not possible in classical physics, and it is a very modern view. If you replace expectation catalog by information, you have a very modern interpretation of the situation. I mentioned the 1960s. John Bell came about with his theorem, which basically says the following. I know it is well known now, but for those of you who know everything, I would like to quote Feynman, who once said, "Never underestimate the pleasure of an audience hearing something they already know." And for the others, it's a small introduction. We consider a source which emits pairs of particles, and the pragmatic or the operational point of view is whenever you measure their polarization, horizontal or vertical. Whenever you observe one to be horizontal, you see the other one is also horizontal. Whenever you observe one vertical, the other one is also vertical. Quantum mechanics says that the state which we use, written down here, is a superposition of both possibilities and not just a statistical mixture. The important point being that before you do the first measurement, neither of the 2 photons carries any well-defined polarization. To the contrary, it assumes completely randomly one of the 2 possibilities, and the other one is then projected onto the corresponding state. Now, this is really the mind-boggling situation. How can two processes, of which we know, the measurements on the two, of which we know that they are completely random in a much deeper sense than any randomness in classical physics, give the same results? That's actually what Schrödinger's point was. And Bell showed that if you look at correlations not polarized as parallel but rotated at slight angles, then you arrive at a limitation of the strength of correlations if these correlations can be explained by what one calls a local realistic viewpoint, namely the assumption that the measurement results A are given by some properties which the individual systems have before and independent of measurement, and B, there is no instantaneous action at a distance. Quantum mechanics says that the correlations are stronger than that, and there are limits for the sums of four pair correlations, which are called Bell's inequality. Limits if the world would be local realistic. Quantum mechanics says that this can be violated. Einstein puts the position in a slightly different way, which is quite interesting. He says that the decision by you as an experimentalist which measurement to perform on the first photon defines whether this first photon will be polarized horizontally or vertical with respect to the direction you choose. And that projects the other photon onto horizontal or vertical to the same direction. So by making the choice here, you basically force the other photon to be in an eigenstate to the direction which you choose here. And therefore, Einstein says quantum mechanics cannot describe the real factual situation. The situation is not like Bertelmann's socks. This is my colleague Bertelmann in Vienna, who was a friend of John Bell. It's a famous picture here. Bertelmann has the feature that he always wears socks of different color. So if you see him come around the corner and you see that his sock is pink, then you definitely know that the other sock is not pink. Now, this is easily explained classically. The article is about quantum socks, where it would be wrong to assume that the socks have the colors before you look at them. This article is written without any equations, without any mathematics, and you can give it to your grandmother, or in order not to be sexist, also to your grandfather. Now, entanglement is popular in the general public. We had the big fun and joy to exhibit this at Documenta, which is one of the biggest exhibitions of contemporary art. It happens in Kassel every 5 years, and we had an experiment on entanglement here. You see a blue laser which pumps a crystal where it begins to become red, and the red beams indicate the two entangled photons. Now, to come back to the experimental situation, a standard line of research is to use entanglement over large distances for various reasons. One of them is that entanglement will be used one day for quantum communication between future quantum computers. Another one is quantum cryptography and the like. Here's the experimental situation on the Canary Islands, the two islands, La Palma and Tenerife, separated by 140 to 150 kilometers. You have to imagine that on both islands you have clusters of telescopes. They are together called the European Northern Observatory. And we were the first ones who asked whether the two sites actually can see each other, so you can communicate directly. So we use this since there are three presentations. I just use words, not the laser pointer. We have on the left-hand side we have a laser which pumps a nonlinear crystal, creates two pairs of photons. One photon is measured locally in some way, whatever way you want, and the other one is sent over a telescopic link to La Palma. There are additional tracking lasers which focus the two things on each other and so on. A parallel line of research which was initiated and pursued to a very significant way by the Chizin group in Geneva is to use glass fibers for this kind of long-distance communication. It turns out that the distance limits are about the same order of magnitude in both cases. Here's a picture again of the situation. To the lower right, just outside of the picture, is the west coast of Africa. Here's the receiving station again, the sending station. I want to mention now a little bit about teleportation because it's related to the notion of information again. Remember, before I quoted Einstein, I quoted Schrödinger saying that the situation in entanglement is that only the information concerning both measurements is well defined, not the information concerning individual measurements. This is completely random. Now, in teleportation, you have a situation where you teleport an unknown quantum state by using an entangled pair. I apologize for the strange language here. An entangled pair. And you project this, the original state and the entangled photon onto one of the two entangled one onto an entangled state. And that way, the information carried by the original state is immediately teleported to the other side. Here are some equations for those of you who prefer equations, but you have to work a little bit on it. The experiment was done it's 97 by Baumeister in my group and in Innsbruck. He is here in the audience. The basic point simply is when you look at the situation in terms of information, it's easily understood. Namely, the original state, the original entangled pair, this auxiliary entangled pair, is characterized by relative information. For example, the statement could simply be that the two measurements, polarization measurements on the two photons will be orthogonal in any measurement basis. This is a possible quantum state. The measurement results will be orthogonal in any measurement basis. Now, when you project the initial state and one from the entangled pair onto an entangled state, which is just, there are 4 maximal entangled states for two photons defined in polarization basis. When you project them onto one of the 4 states, it's like a spin measurement of an electron, of an unpolarized electron. You randomly get one of the 2 results. Here you get randomly one of 4 results. One of the 4 results is again the same state which I mentioned just now, which is called the antisymmetric state, namely the state where the 2 photons are projected no matter in which basis you measure onto orthogonal states. Now the chain of logic is very simple. The entangled pair says the 2 are orthogonal. The projection says the 2 are orthogonal. Therefore, the original and the other pair of the entanglement must be the same, because it's a 2-dimensional spin state. So the 2-dimensional Hilbert space. So the logic is basically simple and it's easy to understand with the notion of information. There has to be classical information because of the randomness of the individual result. Here are some recent results between one experiment done by us on the Canary Island, another one in China on some lake in eastern Tibet, where we, in both cases, teleport over distances of 140 kilometers. And more recent, an experiment on entanglement swapping in over 143 kilometers. It says, it says PNAS 2015 last week. Oh, that's an old slide. I should have written it was sometime I think it was sometimes in October or so, September, October last week. So entanglement swapping is an interesting procedure which has been used in the hands-on experiment for the loophole-free Bell test, for example. It's a very interesting procedure. you have two entangled pairs coming from the sources EPR, and you project one from each onto an entangled state. And then the outer two become entangled, even if they have never interacted with each other. Again, by simple logic, the way I said it before, one can easily understand how the correlations arise in a Schrödinger sense as possible statements about possible future relations of the two outermost photons. Now, this kind of procedure is considered by some as an important ingredient to future quantum repeaters, which might join future quantum computers with each other. The future, again, in some respect, is in space. We are collaborating with the group of Jianwei Pan in China to put sources up onto a satellite, in the end to send two entangled particles to two different ground stations, and that way test entanglement over unprecedented distances, but also establish quantum cryptography on the worldwide scale. The first satellite is scheduled to be launched in June this year. We'll see whether the date holds. Usually in the space experiments you have a delay in the last minute, as you know that, right? Here's a scheme drawn by our Chinese friends. If you have the satellite, which has a connection to a ground station in China, and now the satellite doesn't really stop. But above Beijing, it exchanges information with the ground station in China, and then above Austria, it exchanges information with the ground station in Vienna. And under the assumption that the satellite can be trusted between China and Europe, you can establish a quantum cryptography link between these two locations, for example. So I should mention that we are responsible for operating 4 ground stations in Europe, just for weather conditions and so on. 2 will be in Austria, 1 will be the Canary Islands, and 1 will be on Kefalonia in Greece. Now I come to the recent development of loopholes in Bell experiments. So I mentioned before that we have these correlations, and that they violate the assumption of local realism. The predictions of quantum mechanics violate the assumptions of local realism. Now, there have been loopholes in existing experiments. Loophole meaning that a local realist can save his or her neck by making some assumptions. One loophole is called the communication loophole. It's the assumption that if you do a static experiment, you have a source which emits pairs of particles, or you have pairs of particles entangled in some other way, like in the hands-on experiment. If the experiment is static, sitting there for a long time, then there could be some unknown communication, how the two sides exchange information and establish that way the results of quantum mechanics. In order to violate that, you have to make, or to make it impossible, to make that argument impossible, you have to make use of the fact that according to relativity theory, we have a cosmic speed limit for information, namely the speed of light. So if you decide in the last instances on both sides what you measure, then this explanation is not possible anymore. There was a first experiment about that loophole by Aspect, Dalibar, and others in 1982 in Orsay, where they had 2 detectors separated by about 12 meters and periodic switching on both sides at that time, because it just was all one code 2, but at the time it was a fantastic tour de force experiment. There's no doubt about that. In 1998 in Innsbruck we did an experiment where we had a larger separation and independent random number generators on both sides, and so on. There's a long ongoing story. The other loophole is the fair sampling loophole, which is even more contrived. It assumes that as long as you don't measure all particles, nature could be really vicious. Nature could be such that nature gives you those particles which obey quantum mechanics, and you are tricked in believing that quantum mechanics is true. Now, this is a very strange assumption, but it's logically possible. It turns out that once you detect more than about 2/3 of all events, depending on specific assumption, then you can exclude that explanation. And that has been done first by the group of Vineland in Boulder. But in that case, it was two ions sitting in a trap a few micrometers apart. So in that case, the communication loophole was wide open. In the communication loophole experiments, the fair sampling loophole was wide open. And there's a third loophole, which I personally consider a conceptually most interesting loophole, namely, you have to assume that even when you do have a random number generator here, that the choice on the two sides is really free, it's really independent. That there is no influence from the joint common past which determines the settings. Now this is evidently a very tricky loophole, and I will say about that in a moment a little bit more. That was closed by us for some specific assumption in 2010, but I don't want to go into details here. Now here's the first experiment, closing all loopholes at once, the famous experiment by Ronald Hanson here, who introduced me. This is really, in my eyes, a fantastic experimental tour de force. He can explain it much better than I can. It's about spin correlations in diamonds, and it uses entanglement swapping in the sense that a photon emitted or photons emitted by two NV centers are projected by a beam splitter on an entangled state, and that gives you now the information that the two spins out there have become entangled. This is very important. It's a very interesting feature of the experiment. You turn your detectors only on then when you know that you have an entangled pair. That's quite nice. The experiment, we have a sketch here, is about a distance of 1,300 meters, and you have a statistical significance S. The S value, which was limited by 2, Bell's inequality, was 2.42 plus minus 0.20, and the probability that the results could have been explained by a local realistic theory was 0.039. Now, there was another experiment which was done very recently in November. The first result, it was first announced at the PQE meeting in Snowbird just a week ago. The Harald Weinfurter group in Munich is a conceptually similar experiment to the Hanson experiment. What they do is they have two atoms in a trap, and they do the same kind of idea. They entangle them via photons emitted by the atoms and subject to projected onto an entangled state. Their distance is 400 meters, as you can see here. That's a view of the campus of the university, and their statistical significance is 2.54 plus minus 0.24. It's just about the same as your experiment. I don't know the p-value here, so I don't know, and I cannot give that. But it must be of the same order of magnitude, I would guess. Now, there have been finally two experiments published at the same time in PRL. I should mention that all four groups, we all were in good contact during the experiments. We told each other all the time how far we are and so on. And I remember your desperate mails where you wrote that you think you were just very close and now you are very far away again and so on. But finally you succeeded as the first one. But anyway, we all were in good contact with each other. And as a result, the two papers were published together in PRL recently, one by us and one by the NIST group with some overlap of the authors for obvious reasons, using entangled pairs of photons. These are the two papers here. And our paper has the title A Significant Loophole-Free Test, and I had to insist to physical review to leave this hyphen between significant and loophole, because if that hyphen would not be there, we would call our own experiment significant, which would be embarrassing. So it is just a test of loopholes which we consider significant. That's the point, right? Slightly different. Anyway, and as a result, Fusref Letters was excited by the whole story, and they had a title page. This is a composite picture of John Bell. And if you look then, if you get the issue, these are all small photographs of all authors of these papers, and also of people who contributed early to the field, like Aspe, like Einstein, Bell, and so on, and some of the early publications. Now, I want to say a little bit about these two experiments. The NIST experiment creates two photons at 1550 nanometers and sends them to two detector stations, A and B, which are separated by about 108. Should I use both microphones? Oh, yeah. Okay. Which are separated by 184 meters. The trick now is, in all these experiments, to use an inequality which is insensitive to the detection loophole. That means that if you don't detect enough particles, it's automatically not violated. Now, in that experiment, they use these meandering superconducting detectors, with a much lower times constant than what we had, but with a slightly lower efficiency. They obtained in their experiment a p-value of 5.9 times 10 to the minus 9 as the probability by which the experiments could have been explained in a local realistic way. This was done at NIST. NIST is a government laboratory for standards and technology, and they are actually working on a randomness beacon. Like they have a beacon which sends out time all the time, sends out time signals all the time. They will have a beacon on the internet which sends out random numbers all the time. By really measuring entangled pairs and use one photon as the signal, which tells you that the photon is there, and send the other random signal, random number out. This is a very interesting project. The time scale seems to be 1 or 2 years. You can find it actually already on the internet. Here's our experimental setup. The first picture is an advertisement. Come to Vienna, visit us. What you see here is the Imperial Palace to the right. Back you see the Burgtheater. You see to the left, you see the Parliament, and so on and so on. It's really nice. You should come and visit us. And if you come, visit my group. Okay? Now, why do I show you that? Because of all places, we do the experiment in the second basement of the Imperial Castle, in a place called Corps de Logis, very elegant name, Corps de Logis. I don't know what it means really, but it doesn't matter. And this shows you the basement. We choose it because we thought that the temperature is stable there, but it turned out to be not as stable as we expected, but that's a different story. You see a corridor here. On the floor, the glass, beneath are the glass fibers and so on, connecting the source, which is in the middle here. This little blue box is the open housing for the source. It was closed in afterwards. And at the far end, the small red dot is the cryostat carrying one of our detectors. Here is again the inequality, which is the same basically as the one I just showed you. What we use is use an asymmetric state. It was discovered by Eberhard in the early 1990s that if you use a state where the two terms in the entanglement are not of equal weight, but one is larger than the other, then you can live with lower detection efficiencies. This is quite interesting, actually. The source is shown to the left here. It's called a Sagnac source. I don't want to go into details. It's a periodically poled crystal which is poled from both sides, and the photons are superposed then to go out to the two measurement stations. And the measurement is done by transition edge superconductors. Superconductors operated very close to the transition, and thus one photon can make a big difference in electric conductivity. Here are the results of our experiment. We had a visibility quality of the states of 99%, both for the product state and for the entangled prime minor state. And I don't want to go into too many details here. The p-value is 3.7 times 10 to the minus 31. So that would say that the probability that the results can be explained in the local realistic theory is 10 to the negative 31. Now, this is an unrealistic number, quite clear. It means that any error, any significant error, even if it were a systematic error, even if it were small, would really be larger than what we get here. Okay? So I don't want to go into too many details here. Just to show you the pictures of the three main people on the experiment: Marisa Justina, Søren Wengarowski, and Marijn Versteeg. Why is this interesting? Because a loophole-free Bell experiment is the final proof that secure quantum cryptography is possible. Now, a few small things to round off. According to my schedule here, I have 4 minutes, because I started 1 minute later. So, okay. I told to you that I personally find the freedom of choice loophole interesting. The question is, could even be the random number generators, which are used on both sides, which are quantum random number generators, well, the NIST group also used classical ones, could they be influenced from something in the common past? In principle, it's difficult to rule this out. In these experiments, it was ruled out, the assumption was ruled out that the influence, the unknown influence, which sets the random number generator, could have been created by the source together with the pairs of particles. Okay, that is ruled out. But maybe the cause is something earlier, which we don't know. Maybe something happens at the I don't know, birth of Christ or whatever you call it, which influenced all this, you know? So the question is, how far can you go back? And we are doing an experiment now in collaboration with these people here at MIT, and also with Alan Guth, who is the father of the inflationary universe. So we have our source of entangled particles, and we decide by some information coming from distant objects on the sky which polarization to measure. And it's clear, the further out the objects are, the further back you put the common cause. And the most interesting point is that according to the inflationary universe model, there are quasars out there which share no common cause at all since the end of inflation. So these are the most independent sources you can have. And this is what we are heading for now. Okay, so that's going to be interesting. Now I want to round off with a small discussion of what all this means, besides secure communication or whatever you call it. The question is, what is the consequence? And there, the opinions differ. Some people say that the situation proves that quantum physics is non-local. You have non-local influences from A to B, and there have been even experiments setting, particularly by Gisin, saying that the limit of communication between both sides must be at least 100 times the speed of light. Maybe there's even a higher number now. Okay? I don't believe in this because it's too much of the old-fashioned way of looking at the world. Okay? Another possibility is that the universe is totally deterministic. If that happens, then I would say it's the end of all physics. Why do we do experiments? Because everything is deterministic, and experiment cannot be a question to nature. Another possibility is that there are actions into the past. You can assume that the detectors tell the source back in the past what to emit, which fits quantum mechanics. Now, this is of the same logical position as non-locality. I cannot see, I think they are equivalent. And again, it's an old-fashioned way of looking at the things. It's a way of looking, of asking for a kind of reasonable explanation. One could be a breakdown of Aristotelian logic, which you use in the derivation of Bell's inequality. Another one could be breakdown of counterfactual reasoning, which is that it doesn't make sense to even consider measurement results of experiments which are not performed. So if you say, what would the polarization have been if I had measured this way, not this way? If that kind of consideration is not legal, then you cannot derive Bell's inequality. But then you cannot do many other things in daily life too. In my eyes, it's a combination. We probably have to give up our ideas of space and time. An important message, by the way, is that if you have multi-particle correlations, the measurement results are independent of the relative arrangements in space and time. Completely independent. Doesn't matter whether they are close or far, doesn't matter which is first, which is second, and so on. So this tells us that something about the nature of space and time which we might have overlooked. And we also, because of other reasons, we also have to give up that measurements tells us something in every case. Tells us something, not always. I mean, there are, I want to be cautious, only in specific situations. Tells us something about reality as it exists prior to and independent of observation. Now the question is where to go on. We need a very careful fundamental analysis of the concepts which we are using. You might know, you might be aware of that Einstein appreciated as the most important influence to his relativity theories the analysis done by Ernst Mach on the nature of space and time. That Mach found out that the idea of absolute space and absolute time are untenable. We need a similar analysis for the case of quantum mechanics. And with that, and I hope that someday we will have new physics beyond quantum mechanics, which I predict will be even more counterintuitive than quantum physics. I thank you very much for your attention.